Hello and welcome to lesson 28, where today we are looking at another characteristic of graphs and it's asymptotes. So we're going to be looking at three types of asymptotes and also how to determine whether a function has an asymptote and how that affects the curve on a graph. So our learning goals today is to be able to use limits to analyze behaviors of functions, identify asymptotes, and determine concavity using first and second derivatives. So also just a reminder, when we are writing a limit, if x is approaching c and we have a plus there, it means it's x is approaching c from the right. And if we have x is approaching c with the negative, then that means it is approaching c from the left. And as well, when we look at horizontal asymptotes, plus could mean it's approaching from the top, and the negative means approaching from the bottom. So, starting with our vertical asymptotes, which we've already seen, but just reviewing it now as a explicit definition. So, if a rational function is of the form f of x and p of x equal to p of x over q of x, then this function has a vertical asymptote x is equal to c if q of c is equal to 0, but p of c is not equal to 0. So that means the denominator will give you a 0 result, but not the numerator. And consider if both of them are giving you a 0 result, then that's an indeterminate form, and we've already seen how to work with it. So you would just be factoring out the common term that's giving you zeros, and you might have a vertical asymptote there as well, but we need to investigate it a little bit further. Now consider our first example where we are given the function f of x is x over x squared plus 3x plus 2. And so in this case, we have this is p of x, which is equal to x, and then we have q of x, which is equal to x squared plus 3x plus 2. And so we want to know what values of q of x are giving us a 0 in the denominator, and that's going to help us determine the asymptotes. And we're also asked to describe the behavior of the graph for values of x near the asymptotes, which means that are we approaching infinity or negative infinity? So first, to find the asymptotes, we're going to factor out x squared plus 3x plus 2 to get our factored form, and we get x plus 1 and x plus 2. So that then for this to be equal to 0, either x is negative 1 or x is negative 2. And so we actually have two vertical asymptotes here. And again, the reason for this is we are checking because p of x is just equal to x, then neither of these two values are going to give us p of x is equal to 0. So then it is actually a asymptote because it's only our denominator. Now, to determine the behavior, we can set up a table like this. So just to interpret this graph before we start approaching it, so we want to know the behavior of x as it is approaching both negative 2 and negative 1, which are our asymptotes, from the left and right, and same with this one as well. So we are splitting up our function into three parts over here. This is just f of x, but this is our numerator, and these are the two parts of our denominator. And the reason for we do this, it's a little bit more simple to determine what f of x is instead of inputting this whole function and calculating it several times. Because clearly, for example, for x, I can tell these are all less than 0, so they're negative. You can also choose to just write a negative symbol like that. Now for x plus 2, which is one of our factors in the denominator, again, for values of x less than negative 2, we have that this is negative. So again, negative. But for values of x is approaching negative 2 from the right, this is actually going to be greater than 0, so it's positive. And same with these ones. And as well, we interpret x plus 1, and pretty much what you're doing is just choosing values of x over here. So if I, for example, choose negative 3, then what would this factor give me? Or for example, here, if I choose for this one, for example, x is approaching negative 1 from the right-hand side, then I can choose any value of x that's greater than negative 1, for example, 1, and I'll see that this is positive. And for these ones, you have to interpret the intervals in between these. So for example, here, because I have this following, and I want values of x approaching -2 plus from the right-hand side, I do have to consider this as well. So I'm not just going to pick 10 because we want to consider there is a second asymptote. So perhaps we pick just -1.5, which is in between these two asymptotes. And so again, just having those signs here as well, we have negative, 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 and then this one is positive. And now, for example, let's look at that first row. If you have a negative symbol in your numerator, and then in your denominator you have negative and negative, then overall, this whole uh, expression, which is f of x, is going to be less than 0 or negative. And then you're doing again the same thing for the rest of these. So pretty much two negatives and a positive are going to be positive. Two negatives and a positive are going to be positive here as well. And finally here, two positives and a negative is going to be negative. So now we can tell that as f of x is approaching, and this is just those values of we're trying to determine the behavior of the curve, but now we have this data here as well. So from as x is approaching -2 from the left-hand side, we're going more and more negative, so negative infinity. As it's approaching -2 from the right-hand side, we have positive infinity because of the positive. And as x is approaching -1 from the left-hand side, we have also positive infinity. And as x is approaching -1 from the right-hand side, we have negative infinity. And so try to think right now, what do you think the curve might look like for this function? And so I'm going to show you the curve now, and we're going to be making connections from this table to the graph. So here's the function, and here we have our two asymptotes. So this is x is -2, and this is x is -1. And we can clearly see these values over here shown in our table. So as we are approaching -2 from the left-hand side, we're going to negative infinity. From the right-hand side, we are going to positive infinity. And same with -1 here. We are from the left-hand side going to positive infinity, which is what we saw here. And from the left-hand side, we're going to negative infinity. And so we would be able to, just using this data, be able to sketch our curve based on the asymptotes and the behavior of the curve at the asymptotes. And one thing I want to point out here, and I'll mention again as we're doing this unit, the idea of curve sketching is not to get an exact graph with all the points. You want to get some of your main points or key points and the key behavior of the function, for example, the asymptotes. And based on that information, you want to sketch the curve as best as you possibly can. We're not going to be machines here. We have graphic tools that will give you the exact graph, but if you were sketching the curve with hand, how would you best approximate it based on the characteristics of curves that you know as well as features of the function that you're going to be analyzing? So we also already saw critical points, which would have also, for example, in this case, given us our minimum here, which would be the turning point or the critical point there. Now, just putting all of that ideas together, so we have four different types of vertical asymptotes in regards to limit. Specifically because we have to consider when we are approaching an asymptote from left or right, how that would look like. So if the curve f of x has a vertical asymptote x is equal to c, then we have one of these following limits for sure. So from the left-hand side, we can be going towards positive infinity, or we can be going towards negative infinity from, again, the left-hand side. So notice these two are left-hand side. And then from the right-hand side, we have the same where we can be going towards positive infinity or negative infinity. And in this example, we saw that the behavior is opposite on both sides of the asymptote. So then the limit would be not defined. But if you, for example, had this side going towards infinity as well, we could conclude that the limit of the function as it approaches -2 is just going to be positive infinity because it's from the both hand sides. So we are still using those definitions of limits and for a limit to be defined here, but now bringing derivatives into it as well. And now we are looking at our second type of asymptote. So a horizontal asymptote is now a horizontal line, not a vertical line like like the vertical asymptote. So it's a horizontal line y equals c, and the function's graph approaches a line as x is going towards positive or negative infinity. So as x is getting greater and greater, either in the positive direction or the negative direction, then we are approaching a horizontal line. And this also tells us what we call the end behaviors of the function. So as the function continues on, that's kind of like the end behavior. And what is the curve doing? So for example, consider the reciprocal function 1 over x. So this is also what the curve of it looks like. We're very familiar with this function. And we know that it has a horizontal asymptote y equals 0. And in fact, it also has a vertical asymptote x is equal to 0. And that being said, the behavior from the left-hand side and the right-hand side for the vertical asymptote is different. So this one is going towards negative infinity. From the right-hand side, we're going towards positive infinity. And same with the horizontal asymptote. So as x is approaching positive infinity, we're approaching the horizontal asymptote from the top. But as x is approaching negative infinity, we're approaching the horizontal asymptote from the bottom. An alternative to this would be if you had uh, perhaps a curve like this, and so not this part. Then from the right-hand side and left-hand side, the vertical asymptote is going towards positive infinity, and from the end behavior from both ends is that the curve is approaching the horizontal asymptote from the top. But again, for this example, we have different behaviors. So that's why it's important to interpret also whether you're approaching from the top or the bottom when it comes to horizontal asymptotes, the same way we do for vertical asymptotes where we consider right and left. So how do we find these horizontal asymptotes now? Because it's going to be a little bit different from vertical asymptotes. So consider first this example, x squared plus 6x plus 8. What we do is we factor out the highest degree of x in our polynomial. So in this case, x squared. So that we end up with rational functions here. So 6 over x and 8 over x squared. Now, consider for great or very large values of x, what is happening to this function? So clearly we know that for large values of x, the x squared is going to be growing and growing. But what happens here? So 1 is just 1, it's a constant. But this, because we have 6 on the top, and imagine a huge number here like 1 million. The behavior of this is going to be like 0. It's going to approach 0. And same with here, and even greater because x squared grows even faster at a faster rate than x. So then these two are both approaching 0. So then we are actually only interpreting this value. So we expect the overall behavior of this function to represent the x squared function. And remember, this is our parent quadratic function, which is x squared. So approximately something like this. And again, with curve sketching, this could be moved here or here or here, but the behavior is or the shape of the graph is similar. It's just been translated or stretched somewhere on the graph. So that's exactly what we have here. As x is approaching positive infinity and as same with negative infinity, these two are becoming 0. And this is just also based on the property of the reciprocal function because they are resembling this limit that we just saw here. And so, as x is approaching infinity and negative infinity, the behavior is similar to y equals x squared. And so it is actually approaching positive infinity the same way x squared does. So now let's try with another example. And now here we have a rational function. So You're actually going to be doing the same thing where you're going to factor out the greatest or the x with the greatest degree, but now you have to do it for the numerator individually and then for the denominator individually. So 2x minus 3, the greatest factor for x would be x. And then we also do factor out the 2 because we want a 1 here. It will give us the best interpretation. But even if you don't do that and you just keep it as x, you should get a similar answer as well. So factoring that out, we have 1 minus 3 over 2x, and the same thing on the denominator. The greatest degree of x is just 1, so it's x, and when we factor out, we're left with 1 plus 1x. So again, 1x and 3 over 2x are approaching 0 for large enough values of x, and so we have to look at these two factors. But x over x can be simplified. So then we just have the 2 there. And this is actually why it's important to factor out that 2 because you have the 1s there. So if you don't do it, you would have to do one more step after to interpret this because the reason we did this now, as this limit is approaching infinity, then 3 over 2x will, and this is just distributing the limit using the difference. So this is a difference, we distribute the limit, and this is a constant, so it would be factored out. So then this limit becomes 0, and this limit also becomes 0. And so 1 and 1, this whole thing is just 2. I'll show you, for example, if you hadn't factored as well. So if you had just done x and then 2 minus 3 over x, and then here we had 1 plus 1 over x. So it would be kind of the same thing, but here these two would be factored, or these two would be canceled out. And then when we take the limit here, so consider limit of x approaches positive infinity of f of x, then when we distribute it, this 2 is just a constant, so it's going to stay 2. This would be a 0. And then in our denominator, we have this is just 1, this would be 0. So you would still get 2. But for simplicity, you'll often see the full term for x with the highest degree being factored. So in this case, 2x, and in this case, x. And so we do have that the limit from the end behavior from the positive side is going towards 2. And we were only asked to find the limit as x is approaching positive infinity, but if you also find negative infinity, 2x minus 3, you would also get that this is approaching 2 as well. That being said, as a whole of a function, we still have other parts of it to analyze. For example, I can already see there's a vertical asymptote there, but we were just asked to find this limit, and our work here is done. And now, just for another practice for yourself for what we just did for rational functions, you can practice that x approaches positive infinity of x over x squared plus 1 will be 0. So all you're doing is just factoring out those x values and the x squared in the denominator, and you should get that your overall limit will be 0. Now for this next example, we're finding the horizontal asymptote, but we're also asked to determine whether the graph approaches the asymptote from above or below. And our function is f of x is 7x plus 5 over 2x minus 1, so another rational function here. So again, same thing here, and just to show you, I've also for this one just factored out x, but same process would work. So if we factor out x in our numerator, we have 7 plus 5 over x, and in my denominator, I have 2 minus 1 over x. And the x's are factored out together. So taking the limit now, and first I'm going to start with the positive infinity. Then we know these two are going to become 0, so then really we have 7 over 2. And similarly, from the left-hand side, same thing, and we have 7 over 2. So for sure, this is a horizontal asymptote, but now what is the behavior from the positive infinity and then from negative infinity? How we find this is you pretty much just pick very large values and test it out. So for a x approaching positive infinity, we would pick, for example, 1,000. And so 7,000 plus 5 and then 2,000 minus 1, this is 7,005 over 1,999. So this is greater than 7 over 2. So the graph approaches the asymptote from above because this is because of this inequality where this is greater. So on our graph, actually I'll show you, I have the graph below here. So if this is y equals 7 over 2, we see that we are approaching from the top. So these values are greater than 7 over 2 for large values of x. Now, for x approaches negative infinity, so for example, if I pick negative 1,000, then I have negative 6,995 over negative 2,001. And this is actually less than 7 over 2. So we can clearly see from the graph as well. These values for large values of x in the negative infinity are approaching the horizontal asymptote from the bottom or from below. Now, let's define our horizontal asymptotes as a generalization. So if limit of x is approaching positive infinity of f of x is equal to L, or for x approaches negative infinity, it's equal to L, and the line y equals L is a horizontal asymptote of the is a horizontal line, then it's also the horizontal asymptote of the graph of f of x. So, for example, we just saw these two types of horizontal asymptotes where we are approaching from the top and then from below. So if f of x is greater than L, we say the graph is approaching from above. And if f of x is less than L, we say that the graph is approaching from below. And again, you do have to test for these two limits individually because clearly, as we just saw here, you can have both approaching from above and below for the same function on different ends of the graph. So the end behaviors could be slightly different, but you could also have sometimes that they are also the same. And finally, let's look at our last type of asymptote, which is oblique asymptotes. So we've seen vertical, we saw horizontal, and now we're going to see asymptotes that are diagonal lines. So lines of the form y equals mx plus b, so this is just our straight line, but m is not equal to 0, because if it was equal to 0, then we just have a horizontal asymptote. So if the curve of the function f of x is becoming increasingly close to a diagonal line, such as y equals mx plus b, then we say that that is an oblique asymptote. And as a general rule of thumb, in a rational function, this happens when the degree of the numerator is exactly 1. Oh, exactly 1 more. Maybe I'll underline this one. Exactly 1. 1 more than the degree of the this should be denominator. I'll change that for you. Okay, so consider, for example, this function f of x is 2x squared plus 3x minus 1. The degree of the numerator is 2, because of here. And in our denominator, x plus 1, it has a degree of 1. So this is exactly 1 greater than, the degree in the numerator is exactly 1 greater than the degree of the denominator. So we let p of x be the polynomial in the numerator and q of x be the polynomial in the denominator. And this works for if you had a cubic and a quadratic here, or if you had a degree of 4 and a degree of 3 here, same thing. So we also do check this part for the vertical asymptote. Oh, so because we were asked to find all asymptotes, we are checking all of those. So in the denominator, this would be 0 for negative x is negative 1. But in the numerator, this does not give us a 0 value, so then this is actually a vertical asymptote. And now we also consider the end behavior. So for large values of x, as x approaches positive infinity, and we are factoring now 2x squared and x here. Those are our highest degree of x. And so the behavior of this is 2x. So We would actually say the limit does not exist, or the horizontal asymptote here does not exist because it's a 2x. It's not a constant here. And similarly, for negative infinity, we also see that this is 2x, and so we say that the function does not have a horizontal asymptote because for as x is approaching large and large values, this is going to just resemble 2x, which is not a constant. Now, for oblique asymptote, we actually have to do a process which is divide the numerator by the denominator using long division. So here's my numerator, 2x squared plus 3x minus 1, and this is my denominator, x plus 1. So I look at the first two terms, and here you have to order p of x. So you cannot do um, 2x squared plus, or sorry, minus 1 plus 3x. They have to be in order of the degrees of x. So you have to order p of x in order of degrees. Okay, there we go. So now, x plus 1, and I'm only looking pretty much at the first term. How can I get this to be 2x squared? So it's 2x. I multiply by 2x to get 2x squared plus 2x. This is just also 2x times 1. Now subtracting, I get x minus 1. And so I can't do again, I'm only looking at this first term, which I have x here, so it would only be times 1. So, and then this would give me x plus 1, and subtracting here, and remember this is long division, so these are being subtracted as a whole term. So x minus x, and then negative 1 minus 1 here gives me negative 2. And so we say that f of x, and this is just my long division, so this part is my quotient, which comes from over here. This 2 is my, or sorry, it's negative 2, but I just rewrote it differently, but this is my remainder. And x plus 1 was my divisor. And so I'm just rewriting f of x now, and this is the same idea of factoring out the largest degrees of x, but we have to do it with respect to the denominator, so that's why we do long division. So then, again, for this, we can clearly see that this would be 0 for large values, so really we're only looking at this quotient part. So now, consider the point p of p, which is x, and then 2x plus 1. And this is on the line y equals 2x plus 1. And also consider the point x and f of x, which is going to be on our f of x function. So this is really with this new representation, x and then 2x plus 1 minus 2 over x plus 1. Then we say QP is the vertical distance from the curve to the line. So we're just picking any random, for example, consider this diagonal line, and maybe let me draw my curve a little better. Something like this. So we want to know what the distance from these points on this diagonal line to my curve are. And so we see that for as x is approaching infinity, so the end behavior as x is getting larger and larger, this depends again on the distance from the point on the diagonal line to the function, then this is actually 0. So we're getting closer and closer for large values. And not precisely to say that it's going to become that line, but the distance is almost going to become 0. And same with negative infinity. So perhaps we have also, if I extend this, maybe something like this. Now, these two end behaviors here, or these two parts could be different. So this might perhaps be our vertical asymptote here. Not the best straightly drawn, but something like this. So we have a vertical asymptote there, and then these two are approaching this diagonal line, which is an oblique asymptote. So And that's exactly that interpretation right there, just written out for you. And so we say the function has two asymptotes. So vertical asymptote x is equal to -1, and an oblique asymptote y equals 2x plus 1. And so here, exactly, I've graphed it for you so you see. And f of x is in blue, and my diagonal line is in red. So again, you could see, oh, I drew it a little bit differently. So now exactly, you've seen two different ways that this could be presented, but based on this function, we have our vertical, this one would be y equals -1, or sorry, x equals -1, our vertical asymptote. And this diagonal line is going to be our oblique asymptote. And we can clearly see from here we're approaching infinity, and from here we're approaching the diagonal line, and same with here where our two end behaviors are approaching the diagonal line. And that is a wrap on our lesson for asymptotes. So you saw the three different types. So make sure you are practicing today, especially when it comes to this division of a polynomial by another polynomial. Get some practice with it. So you have a lot of practice questions for today. And as always, if you have any questions, don't hesitate to reach out, and I'll see you all next class.